Okay, today we're going to be focusing on nuclear chemistry. So we've talked a little bit about nuclear energy and power plants, and you've had the option of picking a side for that and arguing for it. Now we're going to discuss a little bit of the chemistry that actually goes on in a nuclear reaction. So here are a few things you want to refresh on. We have what's called an isotopic symbol, or you may have seen it like this with the A's, X's, and Z's. This was like way back from chapter 4 when we were talking about protons, neutrons, and electrons in atoms and how many were present in each atom. This symbol, or the X, remember, is the element symbol, and then we've got the number at the top, which is the mass number, and the number at the bottom, which is the atomic number. If you remember, atoms are based or classified based on the number of protons they have. So their number on the periodic table is equal to the number of protons. So in nuclear chemistry, sometimes we refer to different particles as nucleons, and those are the things that are located in the nucleus of an atom, so our protons and neutrons. And then a nuclide sometimes is referred to as the atoms that are present in a nuclear reaction. So a nuclear reaction is much different than a regular chemical reaction. A nuclear reaction deals with changes in protons and neutrons, and thus changes in the overall mass of an element and the type of element you've got. So what's going to be really important is that you are able to look at this isotopic symbolic notation and be able to understand what these two numbers mean. So again, the top is mass number, so how heavy it is. That's the number of protons plus the number of neutrons. And then the bottom number is the number of protons, or the atomic number. Alright, so let's look at what a normal chemical reaction is. So basically when we have a normal chemical reaction, we're shifting and transferring electrons. So we looked at some ionic compounds forming. We looked at some covalent things. Those are when electrons are shared. It deals with the electrons. When you have a normal chemical reaction, you're not physically changing the types of elements that are there. You're just rearranging those elements to make new compounds, but the elements themselves stay the same. So basically what happens is you start with your element, the nucleus stays the same, the protons remain the same, and thus each type of atom maintains its overall identity. Now, in a nuclear reaction, one thing that we kind of think about are the number of protons and neutrons. And so what we want to think about is this thing called a strong nuclear force. Basically, what that means is atoms stay together. Okay, they don't just implode or explode or change. Somehow they stay together. When you think about the nucleus of the atom, that's composed of protons, which are positively charged. And those are all stuck in the same nucleus. And if you remember, like charges repel each other. So somehow those atoms stay intact. We don't just all of a sudden have atoms exploding because the protons are repelling themselves. So we have what's called a strong nuclear force. That's why the neutral neutrons are in the nucleus. And it basically keeps the protons together in the nucleus, and it kind of keeps them spaced far enough apart so they're in a stable configuration. And that's essentially just called the force, or a strong nuclear force. Hence the picture down here. So let's look at a nuclear reaction. A nuclear reaction involves a change in the atom's nucleus in which a new element is formed. So basically you take your element, for example down here I have uranium, and uranium will decay. That's what we take advantage of in the nuclear power plants. And when atoms decay, we physically get rid of certain particles, and thus changes the actual elements that we've got. So here you can see you've got uranium, and then when it decays, we all of a sudden get krypton and barium. Okay, and we'll look at how some of this works in a minute. Now, we have to think about why this happens. So basically when we get things decaying, it's radioactive decay, and that's when we get radiation, which is what we kind of have in the waste of nuclear power plants. So radioactive decay is basically when you have an isotope of an atom. If you remember, an isotope is a type of the same element, but it's just heavier than the original element. So basically it has more neutrons in it to make it a little bit heavier. So whenever we have an isotope, because it has those extra neutrons, it tends to want to get rid of some of those to get a more stable, get to a more stable state. So when we release those neutrons, that's when we have the radioactive decay, and that's when we start to change what elements we've got. So to start out, atoms tend to want a really equal proton to neutron ratio. So if I find the number of protons and if I find the number of neutrons in an atom and compare those or put them in a fraction with neutrons over protons, I want that ratio or that fraction to simplify really close to 1. Now, elements and isotopes don't always do this. Again, isotopes, remember, have more neutrons than the regular element would have. So they kind of lie all over. And if I look at the proton to neutron count, the highest it'll ever be is 1.5. Ideally, I want it to be around 1 or as close to 1 as I can get. So here is a graph of this. So basically, if I were to take and plot all of my elements, so the number of neutrons and the number of protons, I make those ratios. Some of my elements will fall up here, or some of my isotopes, and some of my isotopes will fall down here. They're not always exactly equal to 1. What they do when they decay is they'll give off certain particles so they can come into what's called a stability region. The stability region is basically where they're the most stable and they have the best ratio of neutrons to protons. So here, this part in blue is essentially where elements like to end up, as close to 1 as possible. And again, in science, it's not always possible to get exactly this ratio, but we want to get as close as we can. Okay, so up here, this is where we have too many neutrons and they tend to radioactively decay, giving away neutrons, and here we may have too many protons. So one way or the other, we're kind of losing one thing to get to that blue spot or the stability region. So there are a few different types of radiation. There's 3 types you'll have to know. The first one is alpha radiation, and that's essentially when you are below the band of stability. So that's when you're hanging out down here and you want to get rid of some of those extra protons and to end up in this blue region. So one of the characteristics of alpha radiation is those elements are typically located below the band of stability, and those elements are usually higher than element number 83. So 84 and beyond are typically the type of elements that tend to decay in this way. So have a alpha radiation that they give off when they do their thing. So therefore, what they give off is then called an alpha particle. So an alpha particle actually looks like a helium atom. Now you just want to remember kind of what it looks like and then what the pattern is in the decay process. So alpha is this Greek letter. An alpha particle has 2 protons and 2 neutrons. So the mass number, again, of that little particle, I take protons plus neutrons. So the mass number will then be 4. Okay. The atomic number, if it has 2 protons, will then be 2. And if I look at the periodic table, element number 2 is helium. Okay, so then that's why there is a helium symbol here, because that's actually what I've got. This alpha particle, this combination. So let's look at a reaction. If I start with, this is radium, and the mass number of radium is 222, and the radium is element number 88 on the periodic table. This isotope of radium isn't the most stable. It doesn't have a very stable proton to neutron ratio, so it undergoes alpha decay, meaning it's going to give off this particle. This is the alpha particle. That's what you want to remember. Here's the pattern. If you're giving off this particle, you're getting rid of this junk, so to speak, the protons and neutrons you don't want anymore. So this overall mass number on radium is decreasing by 4, and the atomic number will decrease by 2. When it does that, we get a new element because we've changed the proton count. I got rid of 2 of them. So if I look at my periodic table, I'll actually bump back 2 spots to element number 86. and that will have a new mass number approximately. Now these are going to be slightly different than what's listed on your periodic table. You just need to know the pattern of what happens here. So let's look at another decay process. The second decay process you can have is what's called beta radiation. So beta radiation is when you are above the band of stability. So here's the stability region. That means you're up here and you've got too many neutrons, basically. Now, beta radiation is a little bit weird in the way that it works. The pattern is fairly easy to remember, but the concept can be a little bit confusing. Basically, for our purposes, you just need to know how it works. So if I tell you something is doing a beta decay, you just need to know the pattern. So it's an element that lies above the band of stability. A beta particle is essentially an electron. So it has a -1 charge, and this is the symbol for beta. There's no neutrons and no protons in this particle. So essentially there's no mass number, or the mass number is 0. And the protons in your element, when you convert it, increase by 1. I know that's a little weird to think about. So basically we kind of emit an electron from one guy, and that's going to change us. That's going to essentially convert to an extra proton. Okay, and that's chemistry we don't really need to get into. You just need to know the pattern. So let's look at this reaction. This is a beta decay. So sometimes they'll use, or I'll try to use this beta symbol. Some books, or sometimes our book, will use an E for electron. Either way, those are the same. So we know it has a -1 charge. Okay, so our proton count is going to change, and we put a little -1 down here. It doesn't have a mass number, the beta particle, so that's 0 up here. And here's what happens. So we start with carbon. This is an isotope of carbon. It's a little bit heavier than what you see on the periodic table. Carbon is typically 12, and this isotope has 2 extra neutrons, so its mass number is 14. When we do beta decay, all you have to know is, since this beta particle doesn't have a mass, the mass of my element here won't really change. And the proton count, or the atomic number down here, will increase by 1. So 6 will go to 7. So I've gone from carbon, and if I go and look at element number 7 on the periodic table, that's nitrogen. And then I have my little beta particle that I gave off to get that. Okay, that's beta radiation. We'll look at a few more examples of that tomorrow. I know that one's a little weird. Okay, the last one is probably the easiest. The last one is gamma radiation, and this is the Greek letter for gamma. A gamma particle is really, really high energy, but it doesn't have any mass, or a mass that's so low it doesn't really affect anything. It's also neutral. There's no charge on my gamma particle, and basically gamma radiation is present anywhere, for the most part, in a nuclear reaction. So beta radiation is basically just any extra energy that's given off during radioactive decay. So gamma radiation, a lot of times, is what's used in the radiation for cancer treatment, as you can see here. So they target cancer cells with gamma radiation. It's used to sterilize food or fruit, things like that. So let's look at a reaction here. If I had this reaction, this is thorium, I believe, and that's going to decay. And this is an alpha particle, so it actually decays by alpha radiation. But then sometimes I can have a gamma particle that may be given off. There's just extra energy there, and that gets lost. And the gamma particle just hangs out kind of on the sidelines here. There's no mass number, and there's no overall little atomic number. It's massless but very high energy. So that's gamma radiation. If I tell you something also gives off a gamma particle, this is what you're going to write down. It's essentially the extra energy present. So to sum up, we've done alpha, beta, and gamma. Alpha is the weakest or lowest kind of radiation, and you can actually use a piece of paper to block an alpha particle. Beta is a little bit more high energy, so you've got to kind of upgrade to a piece of wood. And gamma has the highest energy, and therefore it takes up a concrete barrier to actually block that. So here's a chart just to sum up the different types and what the particles look like and what happens to the mass number in a reaction and the proton or atomic number. We're going to go over examples and practice balancing these types and writing these reactions in class tomorrow. So you're just responsible for taking notes on this video, and there will be a quiz in class on this tomorrow.